Welcome back to Chemistry Matters, Unit 8, and our discussion of chemical thermodynamics, aka thermochemistry. Have you thought of a question and experiment that will allow you to learn more about the hand warmer or cold pack processes? Just as with all science, your question may evolve as you learn more about the process and thermochemistry in general. At the end of this unit, you'll have the opportunity to develop your own cold pack or hand warmer, so you may want to make notes related to the process you're studying as we move through the unit. For now, let's head back to our classroom so we can see how your question and proposed experiment compare to those of our students.
Who'd like to share their question first?
Our question is, how much heat is generated from an instant hand warmer?
We plan to investigate our question by measuring the temperature change before and after activating the hot pack.
Good plan. And later on, we'll learn about the relationship between temperature and heat. And you'll see that we can use temperature measurements to calculate the amount of heat that's been transferred. How about you guys? What did you come up with?
Our question is, why does the cold pack get cold? And we want to answer this by comparing temperature changes caused by dissolving different ionic compounds.
We thought that maybe if we tried dissolving different ionic compounds in water, we might be able to understand why some absorb heat and why some give off heat.
It's good to see that you're thinking like scientists. I can easily imagine that these are the same types of questions that the scientists who made these discoveries were actually asking themselves. Keep your questions in mind as we discuss how scientists study the flow of heat during chemical processes as well as physical processes. When you understand the methods that are used by thermochemists, you'll be better prepared to develop your own plan for developing cold and hot packs at the end of the unit.
Good questions. Were yours similar? Before we go further, let's make sure you're equipped with a thermochemist's vocabulary. Thermochemical changes are usually described in terms of a system and surroundings. The system is the chemical reaction or physical process being monitored. The surroundings are everything else around the system, which might be water, air, packaging, etc. This terminology is important because it's not possible to measure the temperature of chemical reactants and products directly. Instead, scientists monitor temperature changes in the immediate surroundings. All phase changes and chemical reactions are accompanied by changes in energy, often in the form of heat being consumed or released. Exothermic is the term we use to describe a process that produces or gives off energy to its surroundings. Our hand warmers are an example of an exothermic process. The heat exits the hand warmers into its surroundings, causing the surroundings, in this case water, to heat up. Endothermic is the term used to describe the process that takes in or absorbs energy from its surroundings. For example, your hands become the surroundings if you're holding the cold pack. The heat enters the cold pack from your hands. Your hand will actually become lower in temperature during an endothermic process. Notice here that H stands for enthalpy, which is the potential energy of the system. And the change in enthalpy, delta H, is the difference in enthalpy between reactants and products. In the first graph, the reactants have more energy than the products. That difference in energy is released as reactants converted to products. This graph shows an exothermic reaction. The second graph shows the opposite, an endothermic reaction. In an endothermic reaction, the products have more energy than the reactants, so energy was gained by the reaction system. For our purposes, under constant pressure conditions, which are our normal conditions, delta H equals heat transferred, or Q. But it's important to remember that under other conditions, such as in a sealed container that's pressurized or under vacuum, delta H is not equal to heat transferred. Most reactions are, in fact, carried out under constant pressure, which simply means that the process occurs open to atmospheric conditions. The amount of heat transferred during a process is related to the change in temperature and can be measured using a piece of equipment called a calorimeter. A calorimeter is a measuring device in a container that's insulated to minimize heat exchange with the environment. Any heat that's evolved or absorbed during the process will be recorded as a change in temperature. The relationship between heat absorbed or evolved during a process is given by the formula Q equals mc delta T, where Q is the amount of heat absorbed or evolved, measured in joules. M is the mass in grams of the substance gaining or losing heat. C is the specific heat capacity of the substance measured in joules per gram per degree Celsius. And delta T is the change in temperature measured in degrees Celsius. The term I just mentioned, specific heat capacity, is a property of matter that conveys something most of us understand intuitively, that a change in temperature is related to heat transferred. But the concept of specific heat capacity, represented by C in this formula, is a bit more complex and requires further explanation. So let's head back to our classroom so we can see firsthand the important role that specific heat capacity plays in the transfer of heat from one substance to another. For this lab, our students will be recording their observations on forms that you can find in the Chemistry Matters toolkit for this unit. You can use them when making your own notes.
Before I explain what specific heat capacity is, I think it will be helpful to explore its effects. For now, simply use your senses to observe the properties of these two blocks. And so I'm going to give each group 2 blocks, and you have a form similar to the one I have here. And I'd just like you to discuss with your partner some observations that you would make, some similarities and some differences between the 2 blocks.
Well, both blocks are black. That's a similarity.
But feel them. One of them feels a lot colder. I think they're at different temperatures.
This block weighs a lot less. I think they're made of different stuff.
You're right. This one feels like metal, I think. The metal one feels colder. I wonder what this one's made of.
I'm hearing great observations. Let's explore some of those. It looks like that you all noticed that the colors and the shapes of the blocks are the same. And it also looks like you've all noticed that they are made of different materials. So let's talk about that for a moment. Nath Krishna, why do you think they are made of different materials?
Mainly because one of them feels a lot less dense than the other.
Okay, that's a good observation. They are different materials. One is a metal and one is a plastic. What's another difference that you noted? Alexis?
Well, this one feels colder than the other one. The metal one, I think.
Yeah, they're at different temperatures.
Well, I don't think they're at different temperatures because they've just been sitting here in the room. I think the metal one just feels cold. Kind of like how a tile floor feels cold on your feet.
That's an excellent analogy, Nath Krishna, and you're right. Both of the blocks are at room temperature. Would anybody like to try to explain why it is that the metal block feels as if it's at a lower temperature?
I'll bet it has something to do with specific heat capacity, but I don't know how or why.
Well, you're on the right track, Wyatt. So let's try an experiment that might help us understand specific heat capacity better. I'm going to give each group 2 ice cubes. But first, I want each team to predict what will happen when you place the ice cube on the different blocks. Record your prediction on the sheet that I gave you that looks like this. When you're ready, place 1 ice cube on each of the blocks and then watch closely.
I think the ice will melt more slowly on the metal block because it's colder. Well, it's not colder, it just feels colder.
That sounds good. I'll write it down.
What do you think?
I think they'll melt at the same rate because both blocks are the same temperature.
That makes sense. Let's go with that.
Look, the ice on the metal block is melting a lot faster.
That's weird. The metal feels colder. Why would it melt the ice more quickly?
Ours is doing the same thing. How is that possible? Both blocks are at the same temperature.
So take a minute and record your observations, and then brainstorm with your partner to come up with a scientific explanation of what you've just observed. And I'll give you a hint to help you construct your explanation. Every substance has a different ability to conduct heat, which affects how quickly heat can travel through that substance. So when you've agreed on an explanation, draw a diagram representing what happened on a molecular level.
Did you predict that ice melts faster on metal than on other materials? That's really surprising to most people, and it's a mystery that'll take some thought to figure out. Can you think of an explanation? I'll give you some time to develop your own explanation of what's happening. Remember to draw a diagram or a model of what you think is happening on a molecular level. And if you'd like to try this experiment but don't have the exact melting blocks that our students used, you can find a similar experiment in the Chemistry Matters toolkit for Unit 8. Come back and join us for the next video in the playlist after you've had a chance to develop your own explanation and model and carried out the experiment yourself. And we'll compare notes.